Alright, so in this video we're going to talk about work in motion problems. These are problems you've probably seen before, maybe on the ACT or different tests or in other classes you've seen, but this is the application section of our rational functions unit. The main two formulas we're going to use are right here. We're going to use rate equals distance over time and distance equals rate over time, or sorry, rate times time. You can toggle between these two equations by just doing algebra, okay? So for example, if I have rate equals distance over time, to get this equation here, where distance is by itself, I'm basically wanting to get in this equation, I'm wanting to get d by itself. And to do that, I would multiply by t on both sides. And if you look at that second equation here, there's that distance equals rate times time. But anyway, here's a quick example where we use the top equation, just in a basic scenario. If rate is distance times time, rate is another word for your speed. So for example, if I traveled 90 miles, and it took me 2 hours to do it, my rate or my speed is 45 miles per 1 hour, or miles per hour. All right. But we're going to be doing something a little bit more difficult than that. Just want to get a quick intro. All right, so we're going to do 2 work problems and 2 motion problems. Here's example 1. This is from your notes. I think it's the first example. Chad can load a truck in 24 minutes. James can load the same truck in 40 minutes. How long would it take them to load the truck together? I want you to stop for a second, and I want you to just give it your best shot in your head. You can work it on paper somewhere, but I just want to see what you think the answer is. Okay, hopefully you took a minute. I was about to say raise your hand if you think this is the answer, but you can raise your hand if you want. I'd be interested to see how many of you said 32 minutes. Well, why did you say 32 minutes? 32 minutes is halfway between 24 and 40, or the average. This is what a lot of people would say, and if I didn't know how to do this and I had my first guess, 32 minutes would probably be it. But I hope you realize, or hope in a minute you'll realize why that doesn't really make sense here. It doesn't make sense because Chad can load the truck in 24 minutes by himself. He has, let's say he has James helping him. Now James is a slower worker than Chad, but all the work we can get will help. So because James is helping Chad, that 24 minutes should be knocked down to a smaller number. It shouldn't be a bigger number, if that makes sense. So that's why 32, although lots of people will say that, it's not really logical. Okay, so that's the first thing. The way we solve these is we're going to use those 2 formulas that we mentioned in the beginning. So we're going to make I call it a rate times time equals distance. And this is how you'll set every one of these problems up in general. Whoops. All right. So you're going to write down the 2 people you have, or the 2 situations. We have Chad and we have James. One of our equations on that first screen was rate times time equals distance. I want to say that when we talk about distance here, well, what distance are we talking about? We're talking about loading a truck. In this case, distance is synonymous with work done. All right, so don't get confused by that. We'll discuss it as we go. All right, so our job firstly is to fill in this table. So for the rate on these, it's a little bit tricky at first, but it'll get easier as we go. Chad can load a truck in 24 minutes. So for his rate, I'm going to say he can load 1 truck in 24 minutes. If that's the case, that means James's rate is 1/40. If you're thinking, well, I don't know, how am I going to remember that? Okay, remember, rate is distance over time. This number, the ones on the numerators are the distance or the work done, and on the denominator of that fraction, it's the time. Okay, and those, the 24 and the 40 are times. That's how you kind of keep it straight in your head. It's really tempting to write for the times 24 and 40 because those are times. And it seems really simple, but we already talked about 24 and 40 in our rate. For right now, we're going to use just t. How do I remember that? I want you to read the question. It's asking how long would it take them to load the truck together. And so I'm solving for t because it says how long. So I need those variables. Rate times time equals distance. So what I'm going to do to fill in the distance column is I'm going to multiply the rate times time on both. 1/24 times t is just t over 24. And 1/40 times t is t over 40. All right, so I'm going to make a statement here real quick. T over 24 is Chad's work. T over 40 is James' work. Think about whether you agree with this or not, what I'm writing in blue. Chad's work plus James's work equals 1 truck loaded. Okay, that is a true statement. So that's the base we're going to set our equation up with. Chad's work was t over 24. James's work was represented by t over 40. And that gets 1 truck loaded. All right, so this is the equation that we have to solve to find out how long it takes them to load the truck together. All right. This is a rational equation. That's why we're talking about it at this point in the school year of this lesson. I know that the t's aren't in the denominator, but we will get problems where they are. We have fractions here. I want to, for simplicity, there are a few ways to solve for t here, but I want to do the easiest way. And I feel like the easiest way is to multiply both sides of the equation by the least common multiple, like 24 and 40. And that is going to be 120. I didn't leave myself much room. I'm going to write that right there. And 120. Right? How do I find the least common multiple? Just count up by 24 and count up by 40 and do that until you get the same number on both situations and you get 120. Okay, we multiply 120 times t over 24 is going to be 5t. 120 times, we have to distribute 120 times t over 40 is 3t, and 120 times 1 is 120. And from here, we just combine all terms and we solve. T equals 120. Divide both sides by 8. And we get t equals 15. All right. So it takes, when Chad and James work together, it takes them 15 minutes. So when you get answers like this, I want you to think about it. Does it make sense for our situation? One person loads a truck in 24 minutes. The slower person loads it in 40 minutes. If they work together, does it make sense that it takes them 15 minutes? I would say so. Say we got an answer like 29 minutes or 36 minutes or 45 minutes. None of those make sense because those are longer times than the fastest individual. Okay. So just think about your answer when you're finished. And with all application problems, we have to answer in a complete sentence. And so we'll say, oh gosh, one second. if James and Chad load together, it will take them 15 minutes. All right, that's example 1. Example 2 is the same way. We're talking about work, and we're talking about two people working together. Now, if you're feeling comfortable or you want to challenge yourself, you can go ahead and try to work this on your own, but if not, just continue watching the video. This is the same type of problem, but a little bit different in how we actually work it. Every time, though, we're going to take the people or the things that we're talking about, and we're going to make I call them rate times time equals distance tables, but we're going to make a table, basically. Allison, I have Walter. Rate times time equals distance. All right, let's read the question. Allison can assemble 500 pamphlets in 2 hours. Walter takes 3 hours to assemble 450 pamphlets. Working together, how long should it take them to assemble 1,500 pamphlets? Give your answers in hours and minutes. The first thing that should jump out at you is that Allison's rate and Walter's rate are given to us right off the bat. Allison makes or assembles 500 pamphlets every 2 hours. Walter assembles 450 pamphlets every 3 hours. We're going to simplify those fractions in a second, but that part is different based, comparing it to the last example. We are still going to use T and T in this column, just like on number 1, and just like before, we're going to multiply rate times time to get our distance. Okay. And again, distance is another name for it. Okay, let's simplify those fractions. 500 divided by 2 is 250. And if I multiply straight across, I'm going to get 250t. Walter, 450 divided by 3 is 150. And so I'll get 150t. There's our table. Allison's work plus Walter's work, it equals one job done. But one job done here is 1,500 pamphlets assembled. So I'm going to put a 1,500 here. That is different than the last example where we had it equal to 1. You have to be careful. These can get kind of tricky if you overthink it. We have 1,500 pamphlets. Once you have your equation set up, though, this is not too bad. Okay, we have 400t, because 250 plus 150 is 400. And then I just divide both sides by 400. And we get t equals 3.75 hours. If you look at the original problem, it says give your answer hours and minutes. So we don't say 3.75 hours. What we say is 3 hours and 45 minutes. Okay. Answer in a complete sentence. If Allison and Walter worked together, they could assemble 1,500 packets in 3 hours and 45 minutes. I don't know if some of you are, when you're looking at that, you're like, I thought that we said that our answer has to make sense. Okay, here's what I mean. 3 hours and 45 minutes. That's them working together. Allison's time working by herself is 2 hours, which is less than 3 hours and 45 minutes. Walter's time working by himself is 3 hours, which is also less than 3 hours and 45 minutes. So my question is, how are they working together? Their joint time is more than their individual times. The answer is they're making more pamphlets, right? Notice it took Allison 2 hours to make 500 pamphlets. It took Walter 3 hours to make 450 pamphlets. They're trying to make 1,500 pamphlets, which is quite a bit more than this 500 and 450. So it does make sense once you really think about it on that. All right, so that's example 2. We are now going to talk about motion. All right. This example I forgot to mention. The Allison and Walter example is one I pulled from a different resource, so you don't have that in your notes. So you'll need to, when you need to reference this, you need to come back to the video. These next two are on your notes. Okay, so we're going to talk about number 3. Train A has a speed that is 14 miles per hour faster than the speed of train B. Train A travels 400 miles in the same time. That's a typo. The same time it takes train B to travel 330 miles. We want to find the speed of each train. All right. Just like before, we're going to make a table. We don't have names of people now. We have train A and we have train B. But the setup is still the same. I'm going to have my rate times my time equals distance. Now in this case, the distance is actually distance traveled. The first two examples, that distance part meant the work done. That's just a little difference when we go from work to motion. Okay. We're trying to find the speed of the train, which is the rate of the train. So when I go to fill in this rate column, all I can do is say that if train B has a speed of R, train A has a speed of R plus 14, because it says train A has a speed that is 14 miles per hour faster, regardless of what train B's speed is. All we know is that train A is 14 miles per hour faster. We are still going to use T and T for columns T. If you're thinking, well, we're not trying to find the time, that's how we justified using T's on the first two examples. We're trying to find the speed. You're going to see in a minute why we still want to use the time here. Notice we have two variables right now. We have R and we have T. All right. Now on my distance, the first two examples, we multiplied these together to get the distance column. But here, I have distances for train A and train B. Train A travels 400 miles. In the same time, it takes train B to travel 330 miles. All right? So that's what our table looks like for this one. But we are going to use that rate times time equals distance piece in just a second. All right. If I multiply the rate times the time for train A, I get R plus 14 times T, and it's supposed to equal 400. If I do the same thing for train B, I get R times T equals 330. All right, so I haven't done anything too special. I just used the formulas that I've been given. So how am I going to solve for R? I hope we all agree that that's what we're trying to solve for here. We have to do a little bit of algebra. I'm going to solve for T on both equations. if I solve for t on the top equation, I would divide both sides by r plus 14, and that would give me t equals r plus 14 over 400. Oh, backwards. 1 second. I would get t equals 400 over r plus 14. If I do the same thing for the bottom equation, I'll get t equals 330 over just r. Okay, so if you're, well, why are we solving for t? T equals both of these things, technically. And so if that's the case, I can make the case that 400 over r plus 14 has to equal 330 over r because they both equal t. And that's how I'm going to set up my rational equation. I'm going to have 400 over r plus 14. That's an r right there. Let me fix that actually. Equals 330 over r. All right, so here's the equation I want to solve. Okay, we just had to do a little bit of work to get there. I'm going to solve for r. There are a few ways to do this, but I think most of you are going to want to cross multiply. But before you do it, I want to make sure you understand why we're allowed to cross multiply. You can look at this problem and say, well, my denominators are not the same, but if I made them the same, that would make it easier to solve this problem. So that's what we're going to do for a second. Just say we want to make the denominators the same. We would do it by doing this. Okay. Multiplying both fractions by the opposite fraction's denominator. We've done this in class. The denominators are the same, and so for these entire fractions to be the same, if the bottoms are already the same, that means that the numerators have to be the same. So what we'll basically do is cross the denominators out, and I can just solve the numerator equation, which in this case is 400 r equals 330 r plus, looks like that is 4620. Okay, so I went ahead and distributed on both. Okay, now we just solve for r. Subtract 330 r from both sides. We're going to get 70 r equals 4620. And then we divide by 70 on both sides, and we get r equals 66 miles per hour. Okay, make sure you know which train has that speed. Right? That's the speed of train B, because that's where we have just r. So if train B has a speed of 66, that means train A has a speed of 80, because 66 plus 14 is 80. All right. So we answer that in a complete sentence down here. Train A is traveling 80 miles per hour, and train B is traveling 66 miles per hour. All right. And like I said, check your work. If your 2 miles per hour don't have a difference of 14, that means you didn't do it right. Okay, so just check those things. Okay, last example really quickly. Example 4, this one. If you want to go ahead and stop the video and try this on your own, you can. Here we're talking about a plane flying into the wind and a plane flying with the wind. Okay. First thing I want to say is, hopefully you realize that a plane will fly slower if it's flying into the wind versus if it's flying with the wind. If it's flying with the wind, it has the wind aiding it. So it should be going a little bit faster. Okay, so just think about that as we work this problem. An airplane flies 1,062 miles with the wind. In the same amount of time, it can fly 738 miles against the wind. The speed of the plane in still air is 200 miles per hour. Find the speed of the wind. Okay. So for this table, I'm going to make my categories with the wind, and let's call this against the wind. Okay, so hopefully I left myself enough room. We're going to have, like always, rate times time equals distance. Okay. So an airplane flies 1,062 miles with the wind. So on the distance for with the wind, that row, I can go ahead and put 1062. In the same amount of time, it can fly 738 miles against the wind. So likewise, down here, I'm going to put 738. All right. The speed of the plane in still air, when it says still air, that means just no wind at all, is 200 miles per hour. Find the speed of the wind. All right. Let's let W equal the speed of wind. Anytime you define a variable, you need to write will represent. Okay. So if I'm going with the wind, I have that W on my side. So originally I can fly 200 miles per hour, but if I have the wind as an aid, my speed can go 200 plus W, whatever the speed of the wind is. If I'm going against the wind, my speed should decrease by whatever the speed of the wind is. Okay, so 200 plus W and 200 minus W. And then for our T column, we're going to use T and T again. All right, we're going to set up equations just like last example. So we're going to have 200 plus W times T equals 1062. And then we will have 200 minus W times T equals 738. All right. Just like the last example, I'm going to solve for T on both equations. That allows me to set up my main equation that I'm going to solve. Oh, I need to change color. Okay. So when I solve for T here, I get T equals 1062 over quantity 200 plus W. And if I do the same thing on the bottom equation, I'm going to get T equals 738 over 200 minus W. And if both of those things equal T, that means that those things equal each other. And so I can say 1062 over 200 plus W equals 738 over 200 minus W. And I just realized I completely glossed over cross multiplying on that last example. I mentioned it and I just forgot to talk about it. I'll do that now. Okay. On the last example, well, I'll just do it. I'll do it with this example. It's fine. Okay. So if I use the same logic to solve this equation that I did last time, I did this. I basically got common denominators, which is something we have a lot of experience with. Oh, good grief. Okay. Now, the denominators are the same, so now I would just look at the tops. And if you look at the tops, that's what you would get if you cross multiplied. I'm going to show the cross multiplying process in red. Cross multiplying means you do 1062 times 200 minus W, which is what we have right here. Then I would take this 738 and multiply that by 200 plus W, and if you notice, that's what we have up here. So the way I just worked it and cross multiplying are basically the same thing. Cross multiplying just is a little bit quicker. So like I said, I would get 200 minus W times 1062 equals 738 times 200 plus W. Okay. And I would solve from here. I'm going to get, when I distribute here, 200 times 1062 is 212,400. And then we'll have minus 1062W equals 738 times 200 is 14, did it again, 147,600. And then we'll have plus 738 W. When you get the W's all on one side, so I kind of wrote this sloppily, but we're basically going to move this over there and you move this over here. We will get 64,800 equals 1,800 W. And if I divide both sides by 1,800, I will get W equals 36. In this case, the label is miles per hour. In a complete sentence, the speed of the wind is 36 miles per hour. Okay. So those are 4 examples, 2 of work and 2 of motion. If you need more help, if you watch that video and you're just like, that makes no sense to me, feel free to email me and we can talk about it there. We can set up a Zoom session, whatever you need for that. But that is work in motion.